Welcome and thank you for joining. Let's take a look at a couple of examples where we have to create equations of polynomial functions when we're given the zeros or the x-intercepts or the roots of it. So we'll start with example A, where we're given the roots x equals 1, x equals 2, and x equals 3 over 5. First, we would want to list all the roots. Now remember how we solve for the roots or the zeros of a polynomial function. So we normally would have to bring the function to factored form. So we have the factors, 3 of them in this case, and then equal to 0, and we would make every factor equal to 0, or in other words, we would isolate x. So what we have in here is x isolated. So in order to create the equation, we have to reverse the process. So we have to first figure out what factors each root has come from. So in a way, we are kind of unsolving the equation. So to create the factors, we are going to move the numbers to the other side. So if x equals 1 is one of the roots, it means that the factor it has come from is x minus 1. Similarly, at x equals 2, we must have solved x minus 2 equals 0. And x equals 3 over 5 means that we must have solved x minus 3 over 5 equal to 0. Now, as you can see, we have the first factor with integral coefficients, the second factor with integral coefficients, and the last one has one of the coefficients or terms in rational form. Since we're asked to write the equation with integral coefficients or integer coefficients, we are creating, in this case, for the last factor, a new equation with the same roots. And to make the coefficients in integer form, we'll multiply both sides of the equation by 5. So that will change this factor to become 5x, which means 5 times x here, and 5 times negative 3 over 5, which is negative 3, which equals 0 on the other side. So therefore, we're going to say the roots of this polynomial equation are x minus 1, x minus 2, and 5x minus 3. So the equation could have been in the form a x minus 1, x minus 2, and then 5x minus 3. Notice that in the question, you're asked to write a polynomial equation with the given integer coefficients, which means that the coefficient a is not required, so you don't have to write a specific value for it. So any equation or any member of the family of polynomial functions with the indicated roots would make a good answer. So let's continue with the next example, and you can try this on your own if you wish. I'm going to list the roots at negative 3, same process, and x equals 7. So the first factor here will be x plus 3. So again, take the negative 3 to the other side, equals 0. So there goes our first factor here. The second factor would be x plus 1 over 4 equals 0. And the last one is x minus 7 equals 0. So here goes the third factor. And for the middle one here, x plus 1 over 4, we will have to modify it a little. So we'll multiply by 4 both sides of this little equation, and that will create the equation for x plus 1 equals 0 with integral coefficients. So this would be the factor. So create the equation. This is the fun part. Y equals x plus 3, and then 4x plus 1, and then x minus 7. Again, if you're wondering about the coefficient a, we would need another point to be able to find the coefficient a. So any point on the graph of this function. And one of the easier ones to use is the y-intercept, but any other point would do the job. We cannot use the x-intercepts to find the coefficient a because one of the factors will become 0 if we used any of the x-intercepts, so which would result in an equation that we cannot solve for a. Now we'll continue with the third example, and this is where things get a little bit more interesting. So in this case, we are given that the roots are at x equals square root of 2, x equals negative square root of 2, and we are not surprised because, as you can see, these two roots are in radical form, and radical roots will always come in pairs as conjugates or as conjugate pairs. So if we have one of the roots of the equation root 2, the other has to be negative root 2. So what I'm trying to say is that even if we weren't given that the third root in here, so the root of negative root, square root of 2, then we should be able to figure out that if a polynomial function has one of the zeros at root of 2, then the other zero should have been at negative root 2. But in this case, it's a little bit more simple and more straightforward, and we'll list the roots just like we normally do for any polynomial equation, just like in the previous examples. So let's create the factors. So we have x minus square root of 2, we have x plus square root of 2, and x minus 1 over 6. So the equations that we have solved have probably been the equation x minus root 2 equals 0, x plus root 2 equals 0, and x minus 1 over 6 equals 0. So this would be the first factor, the second factor in the polynomial, and we're going to do a little bit of work here so that we won't have fractions multiply both sides by 6, and we have 6x minus 1 equals 0. So this would be the third factor. Now you're probably wondering, why aren't you not changing these two factors to make them with integer coefficients? Now, when it comes to rational roots, yes, it is best that we do this before we create the equation. So we convert rational numbers into integers before we create the equation. But when it comes to radical roots, they eliminate each other, and you will see how and why. So we have y equals x minus root 2, x plus root 2, and then 6x minus 1. Now, if you read the question one more time, it states that we need to find a polynomial equation with integer coefficients. And as you can see here, we don't have integer coefficients, we have radical numbers as well. So what we're going to do is expand the two factors. You probably noticed that in this case, we have the difference of squares formula that we can easily apply, and that will give x squared minus square root of 2 squared, which will be this part of the polynomial equation, and then multiplied by 6x minus 1, which is the other factor. Now, if you simplify it, you get x squared minus 2, and then 6x minus 1. So this equation will have the roots at plus minus square root of 2 and positive 1 over 6. So it satisfies the condition of having the three roots. Obviously, you can add any coefficient you wish. So you can just add a negative 1 here, or you can add a number 2 here. It doesn't really matter. Any member of the family of a polynomial function or polynomial functions with the indicated roots will be a satisfiable answer. Now, we're going to move on and apply this idea to the next example. So let's take a look at the roots one more time. So here we have a root of negative 5. We have a root of 4 plus root 3, and then 4 minus root 3. Again, treat these roots just like you would treat any integral root. So I will list the roots first. X equals negative 5. The next root is x equals 4 plus square root of 3. And the last one is 4 minus square root of 3. So based on the roots, I will start creating the factors. So x plus 5, again, bring negative 5 to the other side, because we know x plus 5 equals 0 is the equation we have had to solve to obtain this root. So next we have x minus 4 minus square root of 3. And lastly, again, minus 4 minus root 3. Excuse me. X minus 4 plus root 3. Excuse me. So y equals Let's expand and simplify. So, if you look at this equation, which is in factored form, it satisfies all the conditions given, then you can tell that for this part of the equation, we have, again, the formula a plus b times a minus b. We can treat as a, x minus 4. Let's make it look like 1. And we can treat as b the root of 3. So let's start expanding. So I will highlight it so it's a little bit easier for us to see it. Okay, so this is our x plus 5. And here we have x minus 4 minus root 3. And x minus 4 plus root 3. So this is the minus, this is the plus. So when you expand, then we have x minus 4 squared and then minus square root 3 squared. Obviously, you can expand this just like you would expand two trinomials, right? So you can take the terms one at a time, but that's longer. So if you follow the pattern that we just discussed, like the x a minus b plus b, it's a little bit shorter and easier. So we have y equals x minus 5. We can expand and simplify x minus 4 squared, x squared minus 8x plus 16. And then minus square root of 3 squared is just 3. So y equals x minus 5, x squared minus 8x plus 15. And voila, this is an equation with the indicated roots. If you want to make it fancy and add, let's say, a coefficient, you can. If you don't, it's still a valid answer. So I hope this made sense, and keep asking those questions and keep working hard. Bye for now. Thanks for learning with me.